All right, recording has started. So, good morning, everybody. Welcome back to Math 115. How's everybody doing this morning? Sleepy. Same. I've really underslept. Seems like most people are pretty tired. Yeah. Okay, well, yeah, I have my coffee as well. You guys probably see me sipping on it every lecture. Okay, so I've been thinking about our class a little bit, and I don't know. I feel like some of this trig stuff lately, I've been getting a little bit too lectury on the class, and I think it's kind of natural for me to default into like a very sort of informative class style, which works well for people who are interested in math, but it can be a little bit boring, I think, for people who are not thrilled by math. So what I want to do today is get back a little bit more towards sort of a course discussion. So I'd like some participation on your all's end to help me kind of go through today's lecture, and it'll maybe slow down the pace a little bit, but I feel like it'll be beneficial for everyone's learning to have a little bit more of a hand in it, as opposed to me just kind of you know giving you guys my word vomit on the subject, which Lord knows I can word vomit a lot about math. So I want to try to not overwhelm you by giving you a ton of information, and I also want to get you guys a little bit more involved in your own in your own class. So we'll start that as soon as I kind of recap what we talked about last time, and then I ask for questions, and then we'll move on to new stuff. Okay? All right, so last time we continued our discussion on these periodic trigonometric functions. Okay, so that was 2 times ago that we did the phase shifts. And the bulk of the lecture was on, well, how do we graph these trig functions? And what I tried to kind of give was an intuitive method for coming up with these graphs. Okay, but I guess if I want you to remember something, well, I'd like you to remember something about the intuitive method of how these graphs come about. Okay, such that if you were stranded on a desert island and you had to do it yourself, you would at least have some memory of how it was done. But I'd also like you to just remember what these graphs look like in general. Okay, so tangent of x, we wind up with this thing which is just kind of like, starting down here in the left by negative pi over 2 and going up to infinity at pi over 2. Okay, and then it just repeats after that. So what I would like you guys to know is that the graph of tangent of x looks like this, okay, in this green box, where the sides of the green box should be negative pi over 2 and pi over 2. Okay, so some instructors, when they teach this section, they wind up just kind of showing you the graphs and saying, okay, memorize the graph. For me, I just really don't like that approach, because I feel like it's just like busy work for you guys at that point. And I kind of like to connect some kind of intuition for what is tangent, because I don't want you to just think that somebody was like sitting in their basement and was like, what if I defined a function called tangent and it was sine of x divided by cosine of x? It's like, no, there's actually a very good reason for this function to exist. It comes from the unit circle, right? It's this length of this tangent line which goes from a point on the circle, okay, for given an angle theta, it goes from that point down to the x-axis, and it exists independently of its definition, okay? It's a mathematical object which is out there, and we simply gave it a name, okay? So I feel like it's more motivating to understand tangent in this way, because if I just tell you, well, tangent of theta is sine theta divided by cosine theta, that's very boring and it doesn't have any meaning. And so I feel like you're less likely to care about it or memorize, or less likely to remember it. And it's also just less fun to memorize a fact than it is to look at a picture and think about the way that the picture looks, So I don't know. That's why I didn't just give you the graphs and say, please memorize these. And it took a really long time to go through them, but maybe that will give you some insight into, why these things are the way that they are. Okay, so that was the tangent graph, which is really the most important one of the three that we learned. And then we've also got cosecant of x and secant of x and cotangent of x. Okay, so for these three, what I would memorize, or what I would take away from this lecture, is they look like these kind of repeated u's and n's. Okay, so going every other one is a u and every other one is an n. Okay, and they are facing up and down respectively, and the difference between cosecant and secant is the same as the difference between sine and cosine, meaning that they are just the same graph moved over a little bit. Okay, so that's cosecant and secant. So, if you want to see how you get the graph, well, you just take the height of the sine function at a given point and take 1 divided by that number, and that's how you get the height of cosecant. Same deal for cosine, and same deal for cotangent, which is then going to look basically like a, is going to look basically like this. In fact, one way you can remember the tangent and cotangent functions is they kind of look like somebody who's like doing a dance. So if this is me, no, don't imagine me. Imagine someone else. Imagine someone else dancing. This one's tangent. And this one is cotangent. Okay. So that's another way you can remember these graphs. Okay, it's tangent and cotangent are the ones that look like people dancing. Okay. And they are going to be offset a little bit, so you do kind of have to remember a little bit what the domains are going to be. But I'm not going to focus in really heavily on that. I just want you to know that these graphs exist and they look like this, and we can learn things about the functions from looking at their graphs and vice versa. And yeah. Okay, and we kind of finished up by talking a little bit more about periodicity, and we were discussing why we should expect tangent and cotangent to be pi periodic. Okay, and the reason was because, well, we have like 6 different reasons for it, but I'll focus on the ASTC reason, if we consider a cycle of going from being positive to being positive again, well, for sine, we'd have to be positive, positive, negative, negative, and the first time we would be positive again after having gone negative would be when we get back to our original first quadrant. But tangent and cotangent have this property that we're going to be positive in the first quadrant, then negative, and then positive in the third quadrant. So the time it takes for us to get back to being positive is basically cut in half. Okay, so that's one way you can view it, and that is why these functions are going to be pi periodic. Okay, and then finally we finished up with this example. Okay, and the goal for this example was to find a value b such that secant of b times x is pi over 3 periodic. We did that in two ways. The first way was kind of algebraic or analytic. Okay, we wrote down, what is secant? We rewrote secant as 1 over cosine, and then we said, well, if those two things are equal, then the cosines have to be equal. And then we used the fact that we knew that cosine of x was already 2 pi periodic to recognize that this statement in the green box here, cosine bx equals cosine bx plus b pi over 3, this requires then that b pi over 3 should be some multiple of 2 pi. So we put b pi over 3 equal to 2 pi, and we found what b should be in order to make our function 2 pi periodic. So that was the analytic way, but we can also view it as a compression, right? If we take a look at the graph of cosine x versus the graph of cosine bx, we know that we shrink the graph horizontally or stretch it by a factor of 1 over b. Okay, so if we want the period to be smaller, then we should choose b such that when we shrink the period 2 pi by b, we get our new period. So that's what we wrote down here. That was 2 pi times 1 over b equals pi over 3. That's what we wanted to be true. Okay, so the left side says we take the period 2 pi and we shrink it by 1 over b, and we get pi over 3. And we just have to figure out, well, what should b be? So that's another way we could have thought about that. Okay, questions about anything we did last time? Okay, just again to recap, I think what we should take away from yesterday's lesson is how to handle periodic functions. We should know what the period of these functions are and how to say things about that. And we should know generally, vaguely, what these three graphs look like of cosecant, secant, and cotangent. And we should definitely know what the tangent graph looks like, okay? Tangent's also the easiest to remember because it goes straight through the origin, okay? And it looks like a dude dancing, or dudette, or non-binary dude. Okay. So if there's no other questions, then let me ask you guys a question. And here it is. The question is the function f of x equals sine of x 1 to 1? Okay. So I hope I can get you guys a little bit more engaged in this conversation. Does anybody have an opinion? On whether we expect the function f of x equals sine of x to be 1 to 1 or not? Okay, Mitchell says no. Any agreement or disagreement among the rest of the class? And one for yes. We're a house divided at the time being. Okay, another one coming in for yes. 3 for yes. Okay. Let's draw the graph of f of x equals sine of x. And then, carries on in that direction. Right, like that. And also in this direction, like this. Okay. So a lot of yeses coming in. Okay, and let me ask, does anybody have an argument for why they think that this function should be one-to-one or not one-to-one? Sam says maybe because it's periodic, it might be one-to-one. I don't believe we stated yet, anyways, any relationship between periodic functions and one-to-oneness. So I'm not sure that argument gives anything to us straight away. Do you guys remember if there were any, oops, we're back in regular mode. Do you know if there was a way that we test for one-to-oneness? Yeah. Okay, Heidi was on the right track. We're getting to these line tests. Okay. There is a vertical there is a line test that we should use to check if a function is one-to-one. And the question is, well, should we use the vertical line test or the horizontal line test? Okay, Heidi says meant horizontal. Okay, does someone remember what the vertical line test was for? What did this tell us? What does the vertical line test give to us? I think Morgan's got it. The vertical line test was for deciding whether or not a relation was even a function or not. So the vertical line test tells us whether the relation defines a function at all. Okay, and I've already sort of glossed over the fact that sine of x is going to be a function. Okay, I've been referring to it as a function for a while now. But you can see that it surely does pass the vertical line test. If we move our vertical line left and right, it's only ever going to cross the graph of sine of x at one point. However, if we have a horizontal line, and our horizontal line is somewhere between 1 and -1, we're actually going to have that our horizontal line, not only does it cross the graph of sine of x at more than one point, it crosses the graph of sine of x at infinitely many points, right? Because this graph goes on and on and on and on forever in both directions, and this graph is just going to keep on intersecting it, okay, this line here. Okay, so the horizontal line test was for saying, well, is a function one-to-one? Okay. So if a function fails the horizontal line test, okay, then we can expect a negative result for the question. Well, is that function one-to-one? Well, we had the horizontal line test and it failed miserably. So in this case, we would say that no f of x equals sine x fails the horizontal line test, and hence is not one-to-one. Is not one-to-one. Okay, so when we have a question like this, we always want to rely somehow on principles which we've earlier learned. Okay, in this case, it was useful to recall the horizontal line test, which told us whether or not a function was one-to-one. Okay, but if you want to give another argument for whether this function is one-to-one or not, then you should try to recall what is the definition of one-to-one. The definition of one-to-oneness was f of x equals f of y if and only if x is equal to y. Okay, which means that, in other words, the height of the function, each height which is achieved by the function is only achieved for one input and one input only. Okay, or you could say f of x is not equal to f of y anytime that x is not equal to y. That's another way you could write it. Okay, so one-to-oneness is about the y values being achieved only once, basically. Okay, so yeah, Mitchell held out against like the whole rest of the class. But for the rest of you who initially thought maybe this function is one-to-one, now is this jogging your memory a little bit in terms of how we figure out whether these functions are one-to-one? Okay. Yeah. By the way, I love that you guys are, brave enough to put your answers in, because it really like moves the class discussion forward, I feel like. And, in my graduate classes, I say things that are like so absurdly wrong all the time. It's just like it's not even funny. Actually, it's pretty funny. So, but that helps me learn, because, then I'm putting forth some thought, and then I'm trying to develop my own ideas, and then saying, okay, that idea wasn't the best, so let me revise myself, and so on and so forth. And it's, it really helps you learn. Okay, yeah, I got the vertical and horizontal line test mixed up. Yeah, that's a super easy mistake to make. So yeah, vertical line test is just for telling us whether the relation is a function. It's been a long time since we talked about whether something was a function or not. So it's definitely easy to understand how you could get those mixed up. Okay, so we've decided that this is not a one-to-one function. Okay? So, follow-up question. I have two follow-up questions. The first follow-up question is, why do we care if a function is one-to-one? Can anybody tell me? Why do we care at all if a function is one-to-one or not? Maybe everyone's nervous now. Yep, that's true. If we know that it's one-to-one, okay, then we know that one input gives exactly one output. In fact, it says a little bit more than that. It says also that one output comes from exactly one input. Does the difference between these two statements get you thinking about anything in particular? The difference between going from inputs to outputs versus the difference between going from outputs to inputs? Okay. Let me put it to you guys like this. If I've got a function here, which takes some values, I know I'm probably making some head spin by reintroducing this notation. Okay, so some of these values go to various different, you know, things in the range. Okay, so here's the range, here's the domain. Okay, some of these are going crisscross or whatever. Okay, and what this statement is saying, if we have a one-to-one function, okay, so the function itself says something about how we go from the left-hand side to the right-hand side. And one-to-oneness says something about the relationship between the right-hand side and the left-hand side. It says that one output can be traced backwards to exactly one input. And we don't have a situation where we have two inputs going to the same output. Okay, that's what we said we don't have. So we have that we can trace back from where we end up to where we started in a kind of nice way. Okay, so there's a topic that we discussed a few times regarding if we have a function which goes from the left side to the right side, then sometimes, depending on the situation, we will also have a function which goes in the other direction. Does anyone remember what that function was called? Yes, that is what I was looking for. An inverse function. Okay, so if we have a one-to-one function, What this says is that, okay, well, if I just erase the arrows which I put on these lines, and I put them in the other direction, then the fact that my original function was 1-to-1 means now that if I go in the other direction and consider f inverse going in this direction, it says something about this function, f inverse. It says that we do not have one input going to more than one output. Okay, we don't have that happening because the original function, which went from left to right, is 1-to-1. We know that if we go backwards, okay, that we're only going to have one output mapping backwards to one single input. And if we have a relationship which has always one input going to only one output, then we know that that is a function. Okay. So it turns out if we have a 1-to-1 function, okay, if we have a 1-to-1 function, then if the function is 1-to-1, then the inverse relation is also a function. Sometimes we use the words, we say the inverse exists. Okay, I'll give you another argument for why this should be true. It'll be graphical this time. If we have a function which gotta remember this properly, which fails the vertical line, horizontal line test. Okay, so say we have this function here, which fails the horizontal line test. Then when we find its inverse, remember we get the inverse by graphing the line or the curve after we reflect it about the line y equals x. So let's look at what the graph of the inverse function would look like. Well, it looks like this. It comes down, is close, and then goes out like this, and then goes around. Oops. It should draw this properly. Come down like this, and then it'll go right through here, and then like this. And what we see, okay, is that since our original function was not 1-to-1, i.e. it failed the horizontal line test, then what happens with our inverse function is that it's going to fail the vertical line test. Okay, so whether or not our original function passes the horizontal line test tells us whether the inverse can have a hope to pass the vertical line test. Okay, so in orange was f inverse of x, and in green was f of x. Okay. So this is why we care about one-to-oneness. Okay. Because the idea is I want to define a relationship which says that, okay, I can give, you know, if you can give me an input and I give you an output, okay, then what you would like to do is give me an output and then I give you back the input. But if you say that the output of your function is is the y value, which lies right here at this red point, okay? So the y value here, well, there's two inputs which correspond to that output. So if you give me the output of that y value and say, well, what's the unique input which produces this y value in this function, then I'm sort of at a loss. I can't really answer your question because there's two places where the function reaches that value. So the question doesn't really even make sense. Wouldn't the inverse pass the horizontal line test? Yes. The inverse function would pass the horizontal line test. Okay, it is one-to-one, but it's not a function. Okay, because it fails the vertical line test. So an inverse function exists if your original function is both a function and it's one-to-one. So although the inverse passes the horizontal line test, we couldn't, for example, recover the original function by taking the inverse of the inverse, because the original inverse function is, although it is one-to-one, it's not a function itself. Does that answer your question, Sam? Okay, so this has been a pretty comprehensive review of one-to-oneness and inverse functions. And the point of all this was to say, okay, sine of x is not a one-to-one function. So how do we make sense of figuring out, well, what is an inverse function for this thing? Should we ever even consider asking for the inverse value of a sine function? Okay, and we do want to end up doing that in some sense. And so here's how we kind of rectify that. We modify the question, basically. We say, well, we know f of x is not equals sine of x is not one-to-one everywhere. But if we just look at it like a little piece of it, then maybe we have a hope. If we just look at f of x equals sine of x, where x is between negative pi over 2 and pi over 2, and actually these should be less than or equal to sines. Okay, then what does it look like? Well, if we look at the graph of this, then here is pi over 2, and here is negative pi over 2. And we look at what sine looks like in this region. Well, it starts at 0 and then it comes up to 1. And then it goes down to negative 1. Okay, and if we ask ourselves, well, is sine of x one-to-one in this region, and we don't consider any other regions, we just consider our vertical or our horizontal line to go across this region and nowhere else. Well, then when we move our horizontal line up and down, we can see that we only ever intersect this line at one single point. Okay, so we do pass the horizontal line test in this region. So the answer is yes, it is. So when we talk about the inverse of a trigonometric function, we are going to limit the scope of our view to a much smaller region. Okay, so we're not really able to satisfactorily answer the question, you know, what angle measurement gives us a certain point on a unit circle, because guess what? For each point on the unit circle, there are infinitely many angles which point at that point. I can choose theta, or I can choose theta plus 2 pi, or I can choose, you know, theta plus 3 pi, or 4 pi, or 6 pi, or whatever. Not 3 pi. 4 pi and 6 pi, but not 3 and 5. Okay, anyways. The point is there are infinitely many angles pointing at that point. So if I want to say which angle points at a given point on the unit circle, I have to specify that the angles should be between a certain range in order to get a unique answer. Okay. So how do people feel about this? Does this make sense why we are restricting our view to this small region of the coordinate plane in order to think about inverses for these functions? Okay, 2 yeses coming in. Okay, good. So, like I said, the overarching question that we're going to answer in the following section is, before we asked, what is the point on the unit circle which corresponds to a given angle theta, and what is the points x and y values? Just say what are the points x and y values? Now we're going to ask the following. Given an x or a y value, how do we find an angle theta such that theta points at a point on the unit circle with x value x or y value y? Okay, and the crux is we need to limit our frame of reference. In order to answer the question in a nice way. Okay, because for any x value which you give me, there are going to be infinitely many values of theta which point at that point on the unit circle which has that x value. Okay, in fact, there's even 2 points on the unit circle which have a given x value or a given y value, so we need to decide between those two as well. Okay. So this is where we're going with all of this stuff. We want to, instead of thinking about, well, I give you an angle theta, tell me the point on the unit circle, I say I give you one of the coordinates of the point on the unit circle, and I ask you to tell me what's the angle theta, which gives me that point. Okay, and this is an inverse problem. We want to invert the process which we were doing before. Okay, is it clear where we're going? All right. All right, well, it's Wednesday, and I'm finally starting week 11's notes, which means I'm a little bit behind, but that's okay. Because I feel like, I don't know, you can go as deep or as shallow as you want in this trig stuff. Okay, so here I'm going to tell you something now. Basically, we have the following. If we restrict the domain of the function y equals sine of theta, or y equals sine of x, okay, and we say that theta should be between negative pi over 2 and pi over 2, then the function is 1 to 1. This is what we just showed in the last example. Okay, what we did was we graphed it. We said, well, between negative pi over 2 and pi over 2, sine of theta looks like this. And it does indeed pass my vertical or horizontal line test. Okay, this is what we showed. So in this small region, our function is 1 to 1. And so in this small region, it does have an inverse. Okay? So what does it mean for this function to have an inverse? It means that if sine of x is equal to y, or sine of theta is equal to y, okay, then we have a function which does the opposite. Okay? Instead of plugging in x into the sine function and getting y, we plug y into the sine inverse function and get x. Okay? And the acceptable values y, which we can plug in to the inverse function, are going to be the possible outputs of the original function. So the domain of the inverse function is going to be, so this is the range of sine of x, and therefore this is also the domain of sine inverse of x. Okay, so the sine inverse function takes as an input one of the y values which can be outputted by sine of x, and it returns the unique angle x, which is between negative pi over 2 and pi over 2, such that when I draw that angle on the unit circle, it points at a point on the unit circle which has the y value which was given. I think that's as concisely as I can put it. Okay, so this is how we're doing this process. Okay, yes, I know. All right, so the last thing I'll just show you really quickly. Okay, if we have an angle, if we have basically, we're given one unique y value, okay? And essentially what we're saying is, okay, let's only consider what's happening between negative pi over 2 and pi over 2. Well, then, if we have a unique y value, it determines a unique point on the unit circle, since I don't have to worry about the point which is on the other side, which has the same y value. Then if you give me that y value, I can use trigonometry to figure out, well, what does this triangle look like? And if I use trigonometry to find out what that triangle looks like, then I can figure out what is the angle which we should put on the inside of the unit circle such that when we draw that angle in the unit circle, it points directly at the point on the unit circle which has the y value which was given originally. So this is the given quantity, and this is the found quantity. Okay, so this is sine inverse, and I will let that marinate on your brains overnight. Okay, and then we'll talk more about inverse trigonometric functions next time. Okay, so starting now and going until 11:30, I'll be having office hours. So if you want me to repeat anything, or if you want to ask further questions about how this inverse stuff works, or if you have questions on any of the homework, then please hang around. Otherwise, have a great day, and I'll see you guys tomorrow. Yep, thanks, Heidi, you too.
Hello, teacher.
Hi.
Just give me 3 minutes. I'm gonna to grab the new notes because I wrote that there, my question.
Okay, sure. In the meantime, Morgan, did you have any questions?
Just going over homework.
Okay.
I think.
Well, did you have a specific question on the homework that you wanted to talk about?
Hey, sorry, I got a call.
No worries.
I know that there was some questions as far as like it was asking me. I want to say it was like secant is greater than something, and it was asking me like quadrants, and I could not figure that one out.
Okay, sure. So we can figure out, I'm guessing it was in which quadrant is secant of x larger than 0, or we can answer all of the following. We can answer secant x greater than 0, cosecant x greater than 0, cotangent of x greater than 0. So on and so forth. Okay, we can answer this for every trigonometric function we have. And also we can do or less than or equal to 0 or whatever. Okay. And it has to do with the following. We just want to use the definitions for each of these. First of all, secant of x is 1 over cosine of x. Cosecant is 1 over sine of x. Cotangent is 1 over tangent of x. Good so far?
Yes.
Okay. And we want to know, when is this fraction giving us a positive number? Well, the numerator is a positive number. So if the denominator is a positive number, then the whole fraction will be positive. Agree?
Yes.
And do you know when cosine of x is going to be positive, and sine of x is going to be positive, and tangent of x is going to be positive?
Isn't that like when
We
I'm
had,
at the diagram, wasn't it like the first quadrant and the third quadrant? Or the fourth quadrant, my bad.
for which one?
When they're positive.
For which one being positive?
I guess cosine, 1 over cosine.
Yeah, this one, 1 over cosine, will be positive in quadrants 1 and quadrants 4, because we have our acronym. Do you remember what the acronym was?
It was like ASTC or something like that.
That's right. So we put the A here. Where's the S go?
Quadrant 2.
Okay. And then T down here, and then C. Okay, so we know where the trigonometric functions, the basic ones, are positive. We know that all trigonometric functions are positive in the first quadrant. Just sine is positive in the second quadrant. Just tangent is positive in the third quadrant. And just cosine is positive in the fourth quadrant. So cosine is a positive number. So if we want to just address when is secant of x larger than or equal to 0, it's the same really as asking, well, when is cosine of x, in other words, the denominator of my function, when is it equal or larger than 0? And cosine of x is larger than 0 in quadrants 1 and quadrants 4.
Okay. So sine, the 1 over sine is positive in quadrant 2, correct?
Yes, and then there's one other quadrant where it's also positive.
3?
Not 1, or not 3.
Hmm.
Where else is sine of x positive? It's positive in quadrant 2, and where else?
1?
Yeah, quadrant 1. All trigonometric functions are positive in quadrant 1.
Okay. And then tangent is positive in quadrant 3 and 1.
That's right. That's
Okay.
right. So let's see if you can answer me the following question. In which quadrants do we have cotangent of x is less than 0?
Would it be in quadrant 4?
In quadrant 4, this is going to be true, right? Because tangent will be negative in that quadrant. So when we do 1 over tangent, we'll divide 1 by a negative number and we'll get a negative number. So 4 is definitely on the list. Any other quadrants?
2?
Yeah, also 2, right? These are the two regions where tangent of x is going to be negative, so those are the two regions where 1 divided by tangent of x will be negative 2.
Okay.
So the answer here is 2 and 4.
Okay.
All right, does that help clear things up a little bit?
Yes.
Okay. It all has to do with this acronym ASTC, which if you want to remember it, it's all students take calculus. Okay? Or you can come up with your own
Okay.
mnemonic device if you want. Okay, so all students take calculus. This is how we remember where the trigonometric functions are positive. And this diagram really only tells us about sine, cosine, and tangent, right? But the other functions are just built from those three, so we can use those things to figure out when those ones are positive too.
Okay. And I'm sure I can find other homework problems that we can go through. I just have to go look at them.
Yeah, sure. Why don't you look? And in the meantime, I'll answer Abdurrahman's question.
Okay.
So, Abdurrahman, are you there? All right, well, I think Abdurrahman's still maybe grabbing his notes. Do you have anything else, Morgan, lined up?
I'm sorry, Professor. I thought I opened the mic. I'm sorry.
Oh.
Yeah. I'm sorry, Professor.
No worries.
Question is, if theta is equal to 3, then theta lies in the quadrant Which quadrant?
Uh-huh.
I just finished, my note, which consists of 300 pages, just by the new one.
I see. Okay,
Yeah.
so if theta equals 3, I'm guessing this is radians. In which quadrant does it lie? Well, let's consider angles. Do you know in which direction does the angle pi face?
Pardon?
The question is, in which direction does the angle theta equals pi face? We have an angle, okay, something like this, right?
Yeah.
How much does it take to go all the way around the circle?
I think half.
To go this angle, this measurement in radians is gamma
2 pi.
equals 2 pi.
Yeah.
Okay, so where is gamma equals to pi? How about pi?
It will be equal to 180 degrees.
Great, and which direction does the terminal side of that angle face? Left, right, up, down, somewhere in the middle? It's to the left. Okay, so gamma equals pi, that's here, going like this. Okay. And pi is equal to what? 3.141596 ... Right?
Yeah.
Okay. How about pi over 2? Let's do beta equals pi over 2. Which direction does that one face? How should I draw it on here? Beta equals pi over 2.
Will gives us like a 90 degree.
Yes, it'll look like this, right? Here's beta.
Right angle.
And beta faces in this direction, right? Straight up. Okay. And if we take the number 3.14159 ... and divide by 2, then we'll get something like, I don't know, let's see what I get if I do it. 3.14 over 2, something like 1.57 ... Okay. So we have, let me maybe draw a gamma with a different color. We have gamma facing directly to the left. And we have beta facing directly up. In which direction do you think that theta is facing? If theta is 3 radians.
I think in the second quadrant.
Yeah, it should be facing somewhere in this region, probably closer to pi than it is to 1.57, right? Okay, so I think this is what the question is asking is well, do you have an idea of how much of an angle is a radian, right?
Yeah.
The other thing you could use is the following. We had a thing that said that like 1 radian is approximately 57 degrees. And then we say, okay, well then 3 radians should be approximately 3 times 57, which would be, I don't know, 21 plus 150, 171 degrees.
Honestly, teacher, I solved it like that. First, I already when I saw theta is equal to 3, I said in the quadrant first, and it gave me a full answer, false.
So you put it
And,
in quadrant 1.
Yeah, first. Then I tried the second method, which is if 1 radian is equal to 57, because it doesn't mention in theta it's equal to 3 radians.
Yeah. So here's the deal. If it says theta equals 3,
Yeah, just 3.
it should be radians.
Yeah.
It'll say theta equals 3 degrees like this if it means degrees. It'll use that this little symbol here. Okay.
Thanks.
So unless otherwise specified by using one of these degree symbols, we're talking about radians.
Okay. Thanks.
Okay. Did you have any other questions?
Yes, I do. Yesterday
Okay.
I couldn't sleep because yesterday I'm trying to graphing like a trigonometric function, and I was confused between when you gave me like an function y equal to 3 sine x plus pi over 8. I was confused between is that meaning we have like a transformation on this function, or it's asking me about to find the amplitude or the period of this function.
Okay, well, we can do both. But first, let me ask Morgan if she has a question. What we'll do is we'll alternate questions one after the other, if that works.
That will be fair. Thanks.
Okay, so Morgan, y'all ready?
I have a lot of questions.
Okay, well, let's do them one at a time and we'll alternate.
Okay. So, all right. So, okay, we'll start at the beginning. There's questions as far as like amplitude. So it says like the amplitude of y equals 6 cosine x is 6, and it's asking me whether it's true or false. I can't figure those out.
Okay, 6 times what?
It's 6 cosine x is 6.
All right, let's see if we can answer this. Okay, do you remember what it means, what the amplitude of a periodic function is? Just in general. That doesn't have to be a super specific answer.
Is like that the height of it?
That's right, it is the height of it. So if we were to draw a trigonometric function, which let me first draw y equals cosine of x. Cosine of x, we should know starts at 1 and then it dives down to 0 and then it looks like this kind of bell shape. And then, you know, carries on, right? In every direction. Okay. And we know that the amplitude is a measurement of how tall the wave is. So let me ask you, which of the following line segments represents the amplitude? Line segment 1 in yellow, or line segment 2 in orange?
Line segment 2.
That's right. Should be line segment 2 will be the amplitude of our function is the height of the wave. Okay, the height of the wave above the x-axis. That's the amplitude. Okay, so what then is the amplitude of y equals cosine of x. What is this height, typically, if we just have a cosine function?
Like 1.
That's right, it's 1. Or if we're down at the bottom, it's -1, right? Okay, so the amplitude of cosine of x is 1. Also for sine of x. Okay? So now let's try to draw the other one. What does 6 cosine x look like? How is it different than cosine x?
Isn't that shifted up?
Well, if we take the height at a given point of cosine of x and we multiply it by 6, then the height of any given point will be 6 times as high as it was before, or if it's low, then it will be 6 times as low as it was before. So the points which are low will get shifted in that direction, and the points which are high will get shifted in this direction. What does that kind of remind you of?
A vertical shift?
Not a shift. A shift would be if both directions went up.
Oh, it's not the stretch then?
That's right. This is a vertical stretch. So here's what it looks like in Desmos. If we do sine of x versus, say, 2 sine of x, or 3 sine of x, okay, or 4 sine of x, or 5, or 10 sine of x, what's happening is it's getting vertically stretched, right? It's like if we had a piece of paper which was made out of rubber, and we literally stretched it up and down, right?
Yeah.
Okay, so ultimately, what's going to happen to a point which was at 1 before? The new height will be what?
6.
That's right, up here at 6. And what about a point which is at 0 before?
6.
Well, if it was 0 before and we multiply that height by 6, what do we get?
0.
0 again, that's right. So again, it goes through this point. And then how about a point which is at -1? So now I'm talking about this point here. Where does it go?
-6.
It goes down to -6, that's right. So our new function looks something like this. You know, and so on and so forth. So, based on this, what do we think the new height is of a wave above the x-axis?
6.
That was
Yep.
Monday afternoon.
So the amplitude of 6 cosine x is 6.
Okay.
So true is our answer.
Okay.
All right, does that make more sense now?
Yes.
Okay. Any other questions about this problem?
No.
Okay. So one thing that I think you need to make sure you can remember is when we multiply a function out front, okay, it corresponds to a vertical stretch, which means things that are beneath the x-axis are pushed even further below. Things which are above the x-axis get pushed even further above, which is why it's a stretch and not a shift. A shift is if we just take the whole thing and move it up or down. Okay, but rather than doing that, what we're doing here is we're actually stretching it. Okay?
Okay.
All right. It's good that you remember that the amplitude is just the height above the x-axis, okay? Good job. All right, Abdulrahman, next question.
Yes, when we have like a function like this, 6 cosine x, when I do know this is a transformation or asking like in a period, you know. Just like an stupid question, but yesterday when I do a lot of graphing problems, and I found the difficulties, you know.
Okay, well, pretty much all of these problems can be viewed as transformations. That is the basis of these functions. Now, we can also understand, because we understand the amplitude and period of cosine and sine, if we transform those functions, we can understand the period and amplitude of the transformed function. Okay, so here's what I can say. If we have y equals sine of x, this function has period of 2 pi and amplitude of 1. Agree?
Yeah.
Let us consider instead the function y equals 3 sine of x. What should the period be?
It's the same.
Still 2 pi. And the amplitude?
3.
Okay, so we can see that a multiplication out front, a vertical stretch, affects amplitude, but preserves period. Okay, here's how we can see that on Desmos, like what I was just doing. If I take a vertical stretch of sine x, the distance from crest to crest hasn't changed.
And that's what we change the range as well.
But we have changed the height of the waves, right? Okay. Now, what about y equals sine of bx? Or why don't we say sine of 6x? What then is the period?
2 pi over 6.
That's right, 2 pi over 6.
Yeah, this is
Because
the second part of my question. I watched some academics YouTube channel. They said whenever you have like an period or a certain function, you just to figure out like 2 pi over b. Is that true?
yes, that is true, as long as this is a b on the inside. As long as it's on the inside, that's true. Okay, so if we have y equals sine of 6x, it makes sense, right? Because this is a horizontal
Stretch.
compression by a factor of 1 over 6, right?
Yeah.
If we graph it using Desmos or just on our own, if we put a 6 in here, what does it look like? Well, it looks much more wiggly, right?
Yeah.
And we can see that the distance from crest to crest here is 1/6 of the distance from crest to crest originally. Okay, it's easier to see it if you make it 2, maybe. You can see that the distance between crests here is half of what it was before. Okay, so if we compress something by a certain factor, then certainly, I mean, if you would just imagine if we had a graph of sine of x, and we have a distance between here and here, if we compress the whole thing, inwards, well, so too does get compressed this distance between my two crests, right?
Yeah. Yeah.
And it gets compressed at the exact same factor. Okay, so if we have a horizontal compression by 1/6, then we have a period compression by 1/6. So you take 2 pi and multiply by 1/6, you get 2 pi over 6. All right?
Yeah.
And what's the amplitude?
It's 1.
Still 1, hasn't changed. No vertical stretch. Okay.
And, yeah, there is a question about the amplitude. Whenever we have like an amplitude, we have to put it in absolute value. That's right.
That's correct. So for example, what does sine of 3x look like? It looks like this, right? Where this height is 3. And if you look at, well, what does -3 sine of x look like? Well, it looks like this, right? So if you want to know, well, what is the height of a wave above the x-axis, you just need to look a little bit further ahead to see that it's going to be the same. You see what I mean?
Yeah.
So when I talk about what is the amplitude, I'm talking about if I look at the graph and I look at the waves and I find one which is rising above the x-axis, what is its height? Okay?
Yeah, when I apply like 3 sine x, I apply it like in -3. Like, but if we ask me like in the height, I just give him like 3 because it's a height measurement. Okay.
Correct, exactly. So we don't really have a meaningful concept of what is -3 meters, right?
Yeah.
It's like I can't walk that distance. I can walk 3 meters, but I can't walk -3 meters. All right. So next up, how about this one? What's the period of this one? Well,
2 pi.
Yeah, 2 pi is right. Because why? What does this actually do? What does the plus pi over 2 do here?
I think we're talking about periodicity.
Not the periodicity here. This is I want to consider this as a transformation of functions. If I do f of x plus a.
Yeah, that will make this function move left or right, but this will means like left.
Yeah, so this one says just pick the whole thing up and move it left.
Yeah.
A little bit. Right? Okay, so the period then is going to be preserved, right? Because if I take sine of x and all I do is I just move it a little bit, then what I've done here is I've taken my original sine function, I've moved it over, here, let me move it over 0.1. Okay, plus, sorry, that's what it should have been, plus 0.1. Okay, well, this is what happens when I move it over by 0.1. It just gets moved a little bit to the left, right?
Yeah.
Or if I move it over 0.3, it gets moved over a little bit more, or 0.5, a little bit more, 0.8. It's just a question of how far to the left do we move it. But you can see that the distance between the crests of the waves is again preserved because all we did was pick the whole thing up and move it over. So in this case, the period is still 2 pi, and how about the amplitude?
That's 1.
Yeah, still unchanged.
Yeah.
All right. So this is how we, kind of consider, well, the overarching theme is we consider all of these as transformations of the original parent functions. if we want to know what the period or amplitude is of the new function, well, we can consider how these transformations are going to affect period and amplitude in the following way. Period is a measurement of what's happening with the distance between two waves. That is clearly going to be affected by a horizontal compression. It's not going to be affected by a vertical stretch of any kind. It's not going to be affected by a shift of any kind. Okay?
Okay.
If we have amplitude, well, this is a measurement of the height of a wave. It will clearly be affected by a vertical stretch or shift. No, it won't be affected by a shift. And it won't be affected by anything going horizontal of any kind.
I got it.
Okay.
I think Morgan have like a question.
Yeah, sure.
Okay, sorry. As far as the period, while we're on it, so I don't have to like spark up new ones. So the question that I'm on says that like -5 plus or -5 cosine of 6, and then it's like x plus pi over 4. So I know that the period. So I've got the amplitude. It's 5, but it says that the period is like 2 pi times 6 because it's 2 pi times b. But it told me that when I put it in that it was wrong. Like it was a right answer, but it was wrote in the wrong way.
Well, what is the... Okay, so we decided amplitude is 5. I think I agree with that. Abdurrahman, you agree too?
Yes, I agree.
Okay. And Abdurrahman, what do you think should be the period of this function?
2 pi over 6, which is pi over 3.
That's right. 2 pi over 6. So, Morgan, we see the 6 shows up in this denominator here, actually. All right. So the reason that happens is when we're multiplying on the inside, okay, this gives us a horizontal stretch or compression by a factor of 1 over 6.
Okay.
Okay. So when it's on the outside, it's like you think. It's just multiplies by the number that you have. When it's on the inside, you have to multiply by the reciprocal.
Okay.
Okay, and it's kind of similar to how, when we do a plus or minus out back, it moves like you think it should. It goes up for plus and down for minus. But when we have plus and minus on the inside, remember it goes like to the left for plus and to the right for minus. You know how it's kind of flipped like that?
Yes.
It's the same thing for this multiplication, okay? When we're outside, when we multiply by a number which is larger than 1, we get a vertical stretch. When we multiply on the inside by a number which is larger than 1, we get a horizontal compression, okay? Because we wind up multiplying by that reciprocal.
Okay, perfect.
All right. So, yeah, go ahead.
So, I don't want to going on for another topic further. I just wanted to finish up with this. If we have like in this function, -5 cosine 6x plus pi over 4. Pi over 4, it means like the phase shift.
Yes.
Okay.
Yes. Phase shift means the exact same thing as horizontal shift. It's just a different word. We use the word phase when we're talking about horizontal shifts of waves. It's just a special word.
I don't want to coming back before the exam by 1 day and ask you what the difference between compound and continuous interest.
Yeah. Well, I mean, did you want to talk about compound and continuous interest now?
No, I think Morgan have a question because I'm still confused why I did mistake on my second exam.
Okay.
Yeah.
Well, we can look at it in a few minutes
Yeah.
here, but Morgan, why don't you give us your next question?
Okay, so the question that I'm looking at right now, it's like cosine theta is equal to 11/61, and theta is in quadrant 4. It's wanting us to find tangent theta. I'm not entirely sure how to do that.
And it says theta is in quadrant 4?
Yes.
Okay, so we have we want to find tan theta. Okay, so what is this telling us? It's telling us we have an angle which is on the unit circle. Okay, this is the first thing we should always do when they're asking us about these things and they tell us where theta is. The first thing to do is to draw a unit circle and to draw an angle which is in that quadrant. So I'm going to draw an angle theta which is in this quadrant here. Okay, and what is the other piece of information they give us? They tell us that the cosine of the angle is 11/61. So what does that tell you that we can what information can we now fill in on our picture?
Radius?
Sure, we could do the radius. What should the radius be? The radius, right, would be this distance from here to here, or if you want this distance from here to here. What do we think? Do you know what point this is on the unit circle? Could you give it?
Yes, sorry. My computer's doing this weird thing where it's like kicking me completely out of Teams.
Oh.
So it's really weird. So that's 2 pi.
The angle would be 2 pi.
Yeah.
But what is the point?
0, 1.
Close.
1, 0.
Yeah.
Okay.
Okay, so what is this distance here?
Wouldn't that be 1?
That's right, this is 1. So if I take this distance here and I just move it down here, what's this distance?
Wouldn't that still be 1?
That's right, still 1. That's the property of the unit circle. That's the reason we call it the unit circle. Unit means 1. So if I draw a line which goes from the center of the circle to the outside of the circle, no matter where I draw it, this length is always 1. In fact, that's the definition of a circle. It's the collection of points which are a certain distance away from the center of a point. Okay. So we have our unit circle here, and we know that that distance there is 1. Okay. Is there anything else we know? What's the other piece of information we're given? We're told that theta should be in the quadrant 4, and the other piece of information is that cosine of theta is 11 over 61. How does this piece of information fit into the picture?
Wouldn't that give us like degrees?
Not degrees. The angle measurement here is on the inside. And so cosine of theta, what does it tell us? If we feed in an angle into cosine, what is the definition of cosine?
1 over sine.
No, the definition of cosecant is 1 over sine. The definition of cosine.
Isn't that x? Or is it y?
No, you're right. Cosine is the x coordinate. So how do I fill that in terms of this picture here?
Wouldn't it be 11 over 61 as the x value and then y as the point?
That's right. This point is 11 over 61, comma y. Unknown y, right?
Yes.
Okay. So what is the one thing that I almost always do when I draw this unit circle? What do I always put inside of it?
Theta.
Yeah, theta, and theta goes inside of another thing. How would I figure out what this y value is?
Not too sure.
Well, if I have a point x, y in the plane, the way I get there is I walk x units to the right and then y units up and down, right? So let's imagine if this is the point 11 over 61 comma y, what I would do first is I would walk 11 over 61 units to the right, and then I would walk y units down. And what does that give me? If I walk to the right and then down, what do we see in here?
The height. Or the right angle.
This is a right angle, and what is this shape here? That's what I'm getting at.
Oh, the triangle.
It's a triangle, right? Yeah. Okay, so this is a triangle. And I know the length of this side is 1, as you already told me. How does 11 over 61 fit into the triangle?
Isn't that one of the, like, angles?
Not one of the angles. Remember, these values here are representing lengths. So 11 over 61 should be the length of one of the sides of our triangle. But which one is it? Should it be the leg on this side or the leg on this side?
I think it's the first one.
On this side?
Yes.
Which this side describes what? How far up and down we go, or how far left and right we go?
Up and down.
Okay, and up and down, which coordinate is the up and down coordinate, x or y?
Y.
Y is the up and down coordinate. So the x coordinate is the left and right coordinate.
Okay.
So the 11 over 61 being in the x coordinate tells us the left and right facing side of our triangle. Does that make sense?
Yes.
So 11 over 61 goes here. And my question to you is, If I know that this side has length 1 and that this side has length 11 over 61, is there a way that I can figure out what the other side is?
Isn't that the... No, it's not the square root.
You're right to be thinking about squares and square roots. Is there a theorem that we have that tells us about the side lengths of triangles?
Is that the 2 square root of 2?
Well, no, so we get square root of 2 over 2 for certain angles of theta, but that's the issue here, is we don't really know what theta is. We're supposed to manipulate this all just using this triangle.
Okay.
Okay, so if I have a triangle here like this, and this side is A, and this side is B, and this side is C, do you know an equation which involves A, B, and C?
A squared plus B squared is equal to C squared.
Very good. So if instead I told you that this side is 1, and this side is 11 over 61, would you be able to figure out what an equation is which involves A?
Would it be A squared is equal to C minus B squared?
Oh, sorry, this should have been a squared, by the way.
Oh.
Yeah, so A squared will be equal to C squared minus B squared. That's true. What is C and B?
Wouldn't that just be... C is going to be 1, and then B squared is just going to be 11 over 61 squared.
Okay, so what's A?
The square root of the sum of C squared minus B squared.
Correct. So we get 1 minus, I don't know, 11 over 61 squared. Just leave it like that for now.
Okay.
Okay, so that's what that side length is, huh?
Yes.
So how do I incorporate that back into this picture?
Once we get the value of A, we can plug that value in for Y.
That's right. So this value of this point here is square root of 1 minus 11 over 61 squared. In other words, it's also the length of this side. This side length is square root of 1 minus 11 over 61 squared. Okay. Okay, now I think we're nearly there. I just need to take the very last step. Okay, so what did I do? Let's take stock. I drew in my angle theta. I made a triangle. I always make this triangle by dropping a dotted line, if you will, which goes vertically to the x-axis, okay?
Okay.
So the vertical line goes to the x-axis, I make a triangle. I use the fact that I know that cosine represents the x value of this point to know that the leg, which deals with distances in left and right, should have the length, which corresponds to the point. Okay, and then I had a triangle where I knew one side length and one other side length, and I had to figure out the other side length. I did that using the Pythagorean theorem. Right?
Yes.
Or you did that using the Pythagorean theorem. Okay, so then we found out what this side length is. So now we have a triangle, and we can figure out what the y value is of this other point. So now what do we have? We have a unit circle and we have an angle which is pointing at the point this is theta, and when the angle theta is pointing at the point 11 over 61 comma square root of 1 minus 11 over 61 squared. So this is P of theta, if you remember. The point on the unit circle which corresponds to the angle theta is the point 11 over 61 comma square root of 1 minus 11 over 61 squared. All right?
Okay.
So how do I find out what tan of theta is?
That's just the sine over cosine.
Okay, and what's
definition. So therefore, it would be 11 over 61 over the square root of 1 minus 11 over 61 squared.
close? The sine of theta corresponds to which value, the x or the y value?
Just kidding. It's the opposite way.
Yeah, the sine is the y value, and the cosine is the x value. So if we want to know the tangent, it's going to be the square root of 1 minus 11 over 61 squared divided by 11 over 61. Or if you want to simplify, you get 61 square root of 1 minus 11 over 61 squared all over 11.
Okay.
All right, so pretty tricky problem. Here's why I think this problem is hard. It asks you to say something about trigonometry without ever even knowing what the actual angle theta is. Okay? The other tricky thing is, even if you could find out what the angle theta is, it's going to be something really weird. Okay, it's going to be some angle like, I don't know. It'll be some angle like 279 degrees or something that's not nice and even. Okay, so that's telling us that rather than rely on the angle, we should rely on the geometry of this triangle instead. And then, once we know the lengths of the sides of this triangle, we should rely on the definition of the trigonometric functions, which the definitions were as follows. If we have P of theta, the point on the unit circle corresponding to the angle theta is the point x comma y, then the definitions were that sine of theta is equal to the y coordinate, cosine of theta is equal to the x coordinate, tan of theta is equal to y divided by x, cosecant theta is equal to 1 over y, secant theta is equal to 1 over x, and cotangent of theta is equal to x over y. So we need to rely on these definitions here to get us to where we wanted to be, and we use the definition that tan of theta would be the ratio between the y coordinate and the x coordinate, which we knew the y coordinate and the x coordinate because we knew the x coordinate already. We knew the radius of this circle is 1, and therefore we had two sides of the right triangle, and so we could figure out what the third side was.
Okay.
All right, any comments or questions?
No, but I did have a question in regards to the exam.
Mm-hmm.
Are we allowed to use a unit circle with all the degrees and radians on them?
Yeah, so like it's open notes. So like if you want to use, let's see if I put it in here somewhere. I think I did. No, it must have been the week before. Okay. Yeah, if you want to like, I mean, this is in your notes. So if you, it's open notes and open book, and you can find this in the notes and in the book. So if you want to have this right next to you when you do the exam, that's fine.
Perfect. Okay.
But you need to know how these points here manifest if you are to say draw a triangle in here. You need to know that these points, the 1/2 here, that's negative 1/2, it means that the x coordinate of this is 1/2. This length here is 1/2, and this length here is the square root of 3/2. As for the length of the side which goes from the center of the unit circle to the outside of the unit circle, you know that one's always equal to 1.
Okay.
Okay. So yes, you can absolutely use this on the exam, but it's not going to get you the right answer most of the time unless you know how to use it.
Okay.
Okay. And for example, I can also ask you questions about the following. If I tell you that there's an angle here which goes to this point, which is not on this picture, and I tell you that this is the angle theta, and I tell you that cosine theta equals negative 1/20th, you need to be able to tell me what is this point, x comma y. And this picture will not help you with that problem. You see what I mean?
Yes.
What you need in order to help you with that problem is the fact that, well, this side length is a radius, so it's 1, and this is the cosine of theta, so I know that the side length, which is here, is 1/20, and so I need to figure out this side length using the Pythagorean theorem, and then you can tell me what the point is, and then if I then ask you what is the tangent of theta, then you'd know that it would be equal to y/x. That's the problem we just did.
Okay.
Okay. So that's pretty much how that works. Okay, Abdurrahman, you had a question about your exam.
No, I think I don't have enough time. I have about 10 minutes.
Okay.
I would rather to ask you to solve a question regarding the homework, which is y equal to the absolute value 10 cosine x/2.
Like this?
There is an absolute value, no?
Around the whole thing? Like this?
Yeah.
Uh-huh. Okay.
I did answer this question correctly, but by guessing, because I know how it looks like the absolute value.
Okay. All right. So would you know how to do the problem if we didn't have the absolute value?
Yeah, I know.
So is the goal to graph it?
What?
What?
No, tell me how it looks like.
Okay. So first of all, do you know how this graph looks like?
Yeah, I have the period 10.
Okay. What should the period and amplitude be?
The amplitude, it will be 10.
And the period?
And the period 2 pi.
Should it be 2 pi?
No, sorry, it will be 4 pi.
That's right. The period should be 4 pi. Because here b is equal to 1/2, so 2 pi over b. 2 pi over b would be equal to 2 pi divided by 1/2 would be equal to 2 pi times 2 over 1 would be equal to 4 pi. Okay, so what does cosine look like? Well, it starts up here. Normally it would start at 1, but in this case it's starting at 10.
Okay.
And then it goes like, you know, down like this, and then up, and then back to where we were. And here we are at 10 again, and this would actually be the point 4 pi comma 10. Right, because we know that this distance, which goes from crest to crest, is the period. You know that distance should be 4 pi. So we know that this point here is 4 pi. This point here is 2 pi, and so on and so forth. Here's 3 pi, and here's pi. Okay? So then, this is what the graph of 10 cosine of x over 2 should look like. If we want to know what does the absolute value of this look like, well, let me ask you, what does the absolute value of sine of a do to the number a?
It's equal to a.
A if a is already positive,
Okay.
and what if a is negative?
Will be a.
If a is negative, so we do like absolute value of -3, what do we get?
3.
3. So if a was a negative number, then the value which we put out is actually negative a. Because -3 is 3.
Okay.
Okay, so what does it say? It says, if the number is already positive, don't change it. So on our graph, if the height is already positive, we don't change at all. Okay?
Okay.
And if the height is negative, if the height is a negative number,
We have to do the opposite thing.
we change the height to be the opposite of what it was before. So in this region, when the height is negative, we're going to replicate this up here. Okay, so the graph of 10 cosine x over 2 in absolute values looks like this. It looks like this, where the distance between here and here
It's the same, I think.
is 4 pi.
4 pi. Yeah.
Okay, but if we wanted to, we could actually take a look at this and say, actually, this function is also a periodic function, except because we made it absolute value, we actually have that what was once a valley is now a crest. Okay? And so now, in fact, we can say that the period of this function is actually 2 pi.
It's like kind of pushing something up across the x-axis.
Say again?
I say like in pushing up something from the x-axis. It's like a reflection.
Exactly. What we do is anything which is
Down.
already above the x-axis, okay, just stays where it is, and everything which is beneath gets reflected up. You're right. This should have been here, though. Sorry. Yeah. You're exactly right. We just reflect everything which is beneath the x-axis, which is, yeah. There's not really a good analog for what this seems like physically, but it's kind of like, if you remember, we also said that the absolute value function another way of understanding this is the absolute value function tells us what is the distance between that number and 0. Okay, so if we're on the number line and here's 0 and here's 3 and here's -3, well, the distance between -3 and 0 is the same as the distance between 0 and 3, right?
Yeah.
And this statement here says, what is the distance between the function 10 cosine of x over 2 and the x-axis? Well, since distance is a positive number, then this distance here is technically positive, even though it's in a different direction. And so when we graph what is the distance here as an actual function, well, the distance will be a positive number, so it goes up here.
Thank you, I got it. I'm sorry for losing my mind last week because I got vaccinated and it was a horrible one.
Oh, yeah. Dang, I'm sorry. But hey, at least you're vaccinated now. That's good. Okay. So any more questions from the homework?
No, thanks.
Okay. All right. Yeah, so by the way, if you want to go over your exam, send me an email and
No, it's not because all the grading. I'm just curious about where I did get wrong about the compound interest because yesterday my brother here in Saudi Arabia have an exam, and I told him I'm really good at compound interest and something like that. I feel like sorry about that. Hoping
yeah.
he did well.
Yeah, so okay. It really would be a good idea for you to schedule a meeting with me and talk it over so that you know it, because compound interest and continuous interest, it'll be on the final exam. So you want to make sure that you know that.
Now I'm going to go over every weekend over the first chapter and the second chapter. When I get there, I will definitely ask you about that.
Okay, sounds good. All right. Well, I will talk to you next time.
Have a good one.
Yep, you too. Bye-bye.